I am recording. Good, excellent. And then I'm going to start this recording. Yeah. Is it? It's probably sufficiently high definition. Yeah. Okay. So we're recording this. We're recording that. I have to start the timer on the phone. This is likely so complicated these days. Okay. So after 25 minutes, it's going to warn me that that camera is going to turn itself off. Have breakfast. Okay, so today we're going to get deeper into excuse me. I may edit that out of the recordings. Okay, so I will scroll down to the bottom of people's comments. So we're going to get into two hard-ish, famous, and not easy problems. So we're going to see, well, actually three, but two of them are sort of the same. We're going to see longest increasing subsequence, edit distance, and building optimal binary search trees. Okay, so it's going to be quite a busy day. If you can follow this, then you should be okay with dynamic programming. Okay? Sort of, except for the stuff I'll teach you next week, which is dynamic programming but using fancy data structures. So maybe you still have to deal with fancy data structures. And I'm going to start off like I did with Huffman's algorithm. I'm going to start you with what looks like a really easy, stupid problem. Like I was doing with the merging lists. Okay. So consider this problem, which I'm going to call ladders, as in like snakes and ladders, which is you're trying to get from one corner. Now, okay, in snakes and ladders, you're trying to get from the bottom left to the top right. I could have done it like this, but I'm trying to get you from the top left, the bottom right, and you want to cross ladders, okay? Ladders are the red arrows. So at each step, you can move right one cell, or down one cell, or diagonally right and down one cell. So you can go from here, you can go to here, you can go to here, or you can go to here, okay? Now, if you do a diagonal down move and you follow one of these red arrows, then you get a point. Okay? The question is, how many points can you get? What is the maximum number of points you can get on your way from here, where you have 0 points, to here, where you have however many? Okay? Is this clear? Can you figure it out? Yeah. Like you can get 4. Okay, yeah. But, so if I put this on an exam, people should pass. But we're going to do that if you had a bigger grid, more ladders, then you want to do this methodically. You want to come up with an algorithm for doing this. So what you would do is figure out what's the max you can get from here by looking at its neighbors. So you would sort of fill in the grid and say, well, if I knew what this value was, I knew what this value was, I knew what this value was, then I could work this out. Okay? So what you could say, if this is, okay, if this is x, y, and z, then well, you have two situations. You have either that, okay. If you don't have a red arrow, then it is max. I should make you do this. And if you do have a red arrow, then what is it? Last, do the, yes, they only go diagonally in this problem. And I apologize for the rather crappy t-shirt I'm wearing. I was just listening to a PhD defense of somebody who's actually virtually coming here as a postdoc. And so it's in Helsinki. I used to work in Helsinki. I was part of the Helsinki Institute for Information Technology, which is terrible because it's abbreviated HEAT. So you'd say hi, and they'd say, "Oh, you're in HEAT," and you'd say, "Yes, I'm in HEAT," which, if you know what that means in veterinary terms, it's actually embarrassing. But so I wore my old I couldn't find my old University of Helsinki t-shirts, so I'm wearing my old HEAT t-shirts. People have 19. There are 8, and now I have one person just left. I have 17 students. Okay, so randomly selecting. Okay. So it's moving on. My pointer is now on Will Robbins. Are you here? Do you have a microphone? Will Robbins? Does anybody have a microphone? Does anybody know what the formula, if I want to work this out, in the case where I don't have a red arrow, it's max of x, y, and z. And if I do have a red arrow, it's what? Okay. Yes, good. Max of x plus 1, y. So, I used to tell my students that the way to think about these problems is, suppose you have this very friendly, slightly weak-willed professor, and so you have the problem, and you're like, "Oh, prof, I don't know what the answer is," and the prof will say, "Oh, well, what would it be if this were this and this were this?" Like, "Well, I don't know what that is," and the prof will tell you, but the prof just has barely enough self-discipline to not tell you the whole answer, but they'll tell you the answer to any smaller subproblem. So I had a biology teacher in high school who was like this. You say, "I don't know the answer to question 2. And you say, "Oh, well, it's like this, isn't it?" So like, "What would it be?" And you're like, "Yeah, I don't know." You say, "Oh, well, it's 7, isn't it?" And you're like, "Yeah, okay, 7. I don't know the answer to question 3 either." So in this case, if the prof told you, like, this is a 3, and this is a 2, and this is also a 3, and then you say, okay, well, this is going to be a 4. Okay, so you can get it. So that's, but then the professor, becomes a little bit, after a while, the exam has gone on a bit longer, and the professor has become more obstinate, and so they're not answering questions here, but they'll answer smaller. So you can work this out if you can work out this, this, and this. You can work this out if you can work out this, this, and this. You can work this out if you can work out this, this, and this. So you can always push it back sort of recursively. Now, the thing that makes this different than recursion is your professor is weak-willed, but not quite so weak-willed that they will answer the same question over and over again, right? So remember I said you can answer this if you can answer this, this, and this. You can answer this if you can answer this, this, and this. So this was x, right? So to calculate y, you ask the professor what the answer to x is. But then to calculate this, you also ask the professor what the answer to x is. Well, the professor isn't going to want to tell you the same thing over and over again. So this is sort of recursion, but a bit more efficient in that you don't solve the same subproblem over and over. You keep a table, and when you find out the answer, you write it down. So, okay, what would we actually do? We would say this is, let's fill in this in, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, this is a 0, this is now a 1. This is a 1 because it's the max of these three. This is now a 1. It can be either from here or from here. This is a 1, and this is also a 1, right? Because either to get to here with 1 point, you can either go down this red arrow and then go across, or go down this red arrow and then go across, or go down this red arrow. And then this is 0, 0, 1, and this is 2, and this is 2, and 2, and 2, right? And if I make a mistake, please correct me. And this is 0, 0, and this is 1, either this way or coming from this. And this is 2, and this is 3, and this is 3, and this is 3, two possibilities here. This is still 0, 0, this is 1, this is 2, either from this or from this. This is 3, this is 3, this is 3, 0, 0, 1, 2, 3, 3, and this is 4. Okay? So, you all understand, right? You all think I'm wasting your time, and this is an incredibly easy problem, and like you can't believe this is in third year. Good. Excellent. I will try not to smile evilly when I say that. Okay, so actually, just like when we did that merging list problem, we were actually solving, we were actually designing Huffman's algorithm. We just solved another problem, which is called longest not increasing subsequence, that's next week, longest common subsequence. Okay. And we just found the longest common subsequence between the strings Canada and banana. Okay? So what are the red arrows? The red arrows are where B doesn't match anything. A matches with this A. And it matches with this A, and it matches with this A. N matches with this N. A matches here, here, and here. N matches with this N. A matches here, here, and here. So I put the red arrows arriving at the cells where I have a character here matches a character here. The ith character was. This is the empty string in both cases. So that's what that's doing there. That's why there's nothing here. So, to remember the dynamic program for finding the longest common subsequence, just think of it as crossing red ladders, okay? Because you can figure that out. Longest common subsequence is a bit trickier, but it's the same problem, okay? Why? Well, let's suppose we have some string, and it's x1, x2, xm, and we have some string y1, y2, but yn, it can be a different length. And we want to look at, so the longest, did I say substring? I mean subsequence. In case I say longest common substring, I mean longest common subsequence. So what is the longest common subsequence of Canada and banana? Well, it's ANAA, right? Because there's an ANA and an A, and ANAA. And it's 4. No, substrings have to be continuous, subsequences don't. Okay. Yeah, okay. So, why, let's consider why we just solved this problem. Well, suppose we have this x1 to xm, y1 to yn, and what we've done is, do we want to have m rows and n columns? Yeah, m rows and n columns. So let's suppose we have, oh no, my marker is dying. So let's suppose we're working out yj minus 1, yj. Can you see this? Maybe not. I use black too much. Okay, so let's go to, so we have x1, xi minus 1, xi, y, y1, yj minus 1, yj. Okay? So this, what is the longest common subsequence of the empty string and the empty string? I only have 18 students. Empty string, what is the longest common subsequence of nothing and nothing? It has length nothing, yes. What is the longest common subsequence of nothing? So y1 to ym can be Canada, and x1s, they happen to have the same length in this case. M and n both happen to be 6. But this could be, you can think of this as banana if you want. So what is the longest common subsequence of the empty string and C? Nothing. And the longest common subsequence of the empty string and anything is nothing. There's nothing in the empty sequence. The same thing here. What is the longest common sequence? So you're going to want to fill this grid out such that cell ij, so this is counting from 0, 0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6, such that cell ij contains the length of the longest common subsequence of x1 to row and then column, xi and yj. So let's suppose that you've filled in all the rest of this, and now you want the length of the longest common subsequence of x1 to xi and y1 to yj. Well, how do you get that? So you can think, if I have like Kana and Ban, so what I can have is let's say Bana. If the ith letter in this string, no wait, this is the one along the top. So I want it to be the jth letter here. Okay, so this is Bana and Kana. If these letters match, then I have the option of saying, if these two letters match, then I can take the longest common subsequence of these strings, and then I add 1, right? So if these two letters match, then I have a red arrow here, and I have the option of taking this and adding 1. Or I can say, maybe I'm looking at banan, and this, I say, well, I want this character to, the ith character here matches to an earlier character here, so I ignore the character, and I keep this subsequence that, say, is like this. Okay? So if it's the case that the characters match, I can take this and add 1. Or if they don't match, then I can just take whatever subsequence existed and I don't choose them. Or I can take the subsequence in this that matches to some earlier part and I can throw this character away. Or what I can do is match these two. Yeah, I can have an n, and I can throw this away, right? Okay, so let's actually do this. So we want Bana and Bana. Let's say we have one Bana. Okay, so I is 1, 2, 3, 4, 5. J is 1, 2, 3, 4. So what is is, so here is, if we're in this case, because these two don't match. So what is this one is, so this is 5, 5, this is 4. So what is 4, 3? What is the longest common subsequence of bana and care? It's 2. Okay, I'm just going to stop the video and start it again. And it's going to process for a couple of seconds. We have 45 minutes of recording left. I have 55 minutes. Wrong pin. Can you see my? No, okay, that's off camera. Good. So we're starting again. So let's say in this case, this is, somebody said 2. 2, yes, it's 2 because it's an, right? If it's da and kana. And what if it's 4, 4? So it's bana and kana. Yes. 3. And what if it's 3, 5? Wait. This is 5. So it's I, this is I, and J, right? So 4, 3. No, 4, 3 is 4 and 3. 4, 4 is 4 and 4. And then there's 5, 3. 5, 3, banan and kan. It's still 2, right? Because banan, you can only get, so there's five characters here. Banan and kan, well, it's only A and N, so it's still 2. So this, it can be either, so banan and kana is either so we either have bana and kana, or we have banan and or we have 4 and 4 is bana and kana. So here we have A and A, A and A. Here we have, say, AN and AN, and here we have, wait, I've got bana and kana twice. We've got 5, 5, 3, 4, 4, and 4, 3. 4, the sheet here. Okay. So, which is best? Well, to take this and put an N and not it with anything. So the longest common subsequence of banan and kana is ana, still. Right? It's like you're trying to get from here down to here, and every time you cross a red bridge, it's because you've managed to get to a position where you have a character here that matches with a character here, and you get a point. You add the same character to both of them, and you increase the length of the longest common subsequence. Okay, so this is max of this, this, and this. This is 3. And that's because the longest common subsequence of this and this is Anna, and that you get, I'm not going to put a red arrow there, that you get because it's the same as the longest common subsequence of Bana and Kana, 4 and 4. Okay, so let's look at the case, let's look at the other case, because I really want you to understand this stuff. Let's look at the case where it's banana and Canada. This is this case where the two final characters do match. So this is I equals 6, J equals 6. Okay? So what is this matrix? What are these entries? Well, this is the longest common subsequence of I is equal to 5, I is equal to 6, J is equal to 5, J is equal to 6. This is 5 and 6, so this is the longest common subsequence. Here we put the longest common subsequence of banana and canard. And that's 3, because it's still A and A. And here we put the longest common subsequence of banana and canard. And that's still 3. And here we put the longest common subsequence of I is 6 and J is 5, banana and canard. Yeah. Okay, I may have said banana and canard when I meant banana and canard. Okay, so this is still 3. But then here we take this, how do we take? We take the max of this plus 1 and this, and we get 4. And why is that the case? It's because the longest common subsequence of banana and Canada is the longest common subsequence of banana and canard with an A appended to it. Okay? Good, excellent. 2 people will pass my course. As I've said in the previous lecture, you should, well, I didn't say you should code this, but in general, if you really want to be sure you understand something, you should code it. So, like, right up, it's 2 for loops. Just have it do this. So that's longest common subsequence, which I will occasionally say longest common substring, which is wrong, because a substring has to be continuous, a subsequence doesn't. I'll also sometimes probably say longest increasing subsequence, because that's what we're going to study next week. Okay, longest common subsequence, I think that might be on LeetCode. If you can find it on LeetCode, solve it on LeetCode. It's related to another famous problem, which is called edit distance. So it's sort of a flip side of edit distance. So edit distance is there are lots of different kinds of edit distance. But what's usually said is you're given two strings, like banana and Canada, Canada and banana, and you're asked how many edits does it take to change one of the strings into the other one. Where in edit, you can insert a character, you can delete a character, or you can change a character. Okay? It's very close. You also do it with the same kind of dynamic programming, but so this is called the recurrence, because people love using recurrence for several different things in the same course. It's slightly different recurrence. I'm still going to use the same matrix, and I'm still going to have the same red bridges. You can be thinking of questions while I erase everything. The philosophy, so what changes is, now, longest common subsequence, I'm gaining a point every time I cross a red bridge. Okay, so I'm going to change this problem definition slightly. The idea with the longest, so with longest common subsequence, you're looking for stuff which is the same, and for the stuff which is the same, you gain some sort of profit. Okay? You try to maximize the number of red bridges you cross. Edit distance, you are trying to minimize the number of edits that you have to do. So the idea, I mean, you can see how this is related, because what you could do is, given banana and Canada, if you know that the longest common subsequence is A, well, what you could do is take banana and get rid and delete all the characters. Now, this is if you couldn't do substitutions. What you could do is delete the characters to get the longest common substring, and then insert the characters, so delete the characters from banana that aren't in the longest common substring, and then insert the characters that in Canada that aren't in the longest common substring. So you turn banana into the longest common substring, and then you turn the longest common substring into Canada. But you can do substitutions, so it's not quite that easy. That would be if edit distance were the version without substitutions. But you can see that there's this idea that if there's a long common substring, then it means that if there's a long common subsequence, then you should be able to get from one to the other. The edit distance should be small. My bagel is like right there. So I was watching a PhD thesis. I wasn't eating. So although it was on Zoom, I was muted, so I could have been eating. So the idea is, now I'm trying to get from here to here. At each step, you can move right one cell, down one cell, or diagonally right and down one step. But you don't pay whenever you follow a red arrow. So how little can you pay? I have to put in here
Otherwise, you pay $1.
Okay? So now, now you're trying to, here you start off, you have paid nothing. And here you're trying to figure out how do you get here paying the least you can. And, well, it's pretty obvious that you have to pay 1 to here, and then nothing, 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 and then 1 to go here, and then nothing. So you can pay 2, right? Which is changing this B into a C and changing this N into a D. So you can, with 2 edits, you can get from banana to Canada. But let's actually figure out how we should do this in general for big, big problems. And people do this. This is used for genetic alignment. So, for example, if they're sequencing a new species and they want to figure out how its genome aligns, that is like you trust me, this comes up in computational genomics. So let's actually see. If you knew how much it cost you to get, what's the minimum price you could pay to get here, or you could ask your friendly professor, Prof, how much does it cost me to get here? How much does it cost me to get here? How much does it cost me to get here? Well, now, what are these recurrences? Now, what is this number? So the 2 cases, so now what is this? Yes. This one is min x plus, well, okay. X, y, z plus 1. And this is min x, y plus 1, z plus 1. Okay? So this is pretty easy. 1, 2, 3, 4, 5, 6. I don't need any recurrences to figure that out, because how many edits do I need to change the empty string into C1, CA2, CAN, 3? Okay. 1, 2, 3, 4, 5, 6. And then to change B into C, well, this is min of this plus 1, this plus 1, this plus 1. So this is 1. This is 2, right? Because you could change a B into a C. So that's actually either I change, I insert a C, and then I change the B into an A, or I change the B into a C, and I insert an A. So this is min of this is 3, this is 4, this is 5, this is 6, this is min, this is 2. This is still 1, right? Because how do I change BA into CA? Well, I just change the B into a C, and then I leave it alone. So I'm still working, if this matrix is a two-dimensional matrix, Aij should be the edit distance between x1 to xi and y1 to yj, right? So this is still, the edit distance between BA and CA is still 2. It is 2, sorry, is 1. BA and CA. Okay, BA and CAN, the min of these 3 plus 1 is 2. Now the min of these 3 plus 1 is 3, and that can be done one of two ways. Either I take B, and so I would go here, so I would change the B into a C, and then leave the AN, and then insert AN, and then this A is an A, right? So it's like I change, what is this? This is BA and CA, BA into CANA. One at a time. Half an hour, maybe. So what I can do is first I change it into CA, and then I insert excuse me, to get to here. So I have the option of either changing B into CAN, is or so it's either I leave it like this and insert AN, or I can take BA and change it to CA and then add NA on the end, right? So I can either insert AN between the C and the A, or I can leave this A alone. Well, I can insert an N and an A afterwards. So it's the same, right? It gets me the same place, but it's two different routes. So the thing I want you to notice is that you can calculate the paths through, you can find the paths through here, and those correspond to strategies, to sequences of edits that you would do to change this string into this string. Okay, so because the search problem, if you get this number down here, that just tells you the minimum number of edits. It doesn't tell you the list of the minimum. It doesn't tell you a list of this to do, right? So in computational genomics, you don't want to know that the distance between this gene in the gene in the mouse and the gene in the human, that the edit distance is this. You actually want an alignment. You want, it's called a cigar string. You may have seen them. Otherwise, look up cigar string and look for one that looks like it's DNA. If this were a normal class, other people would be doing this. But okay, so this is a 4, and this is a 5. And it's a 5 because, and you have two different ways of getting it, either from here or from here. Okay, I'm not going to spend any more time filling in this matrix because it's I'm sure you can do this. I hope you can do this. So that's edit distance. Do you have any questions? Is anybody listening? Of my massive 19 students. Good, okay. So there is, it's not known how to do this. So how long does this take? So each of these steps is pretty easy. But if I give you a string of length n and a string of length m, it's going to take, how big is the matrix? So these are constant, but the matrix is m by n. Right? So in general, it's going to take me order mn time and order mn space. It's going to, if I fill in this matrix, it's going to use quadratic time and quadratic space. Now, I just said that we use this in computational genomics. You align like the mouse genome to the human genome. Well, actually, you align chromosomes. Well, you align genomes. Yeah, ignore it. I mean, you could align whole genomes in microbes. Yeah, whatever. Genomes are pretty big, right? So it's like a human genome is 3 gigabytes. It's 3 billion characters. So if you're looking at 3 billion times 3 billion, that's a lot. So your computer doesn't have that much memory. So first, let's see a quick, what? Already? That was 25 minutes? Still busy, is thinking, okay, now it's restarting. I have only 20 minutes before this recording cuts off. So the first thing is, we can reduce the space. Because notice that once I've computed this row, I'm never going to look at the rows above it before. So if I just want to know the number here, then I can throw the stuff away above this row once I've computed this row. So in fact, I'm only keeping one row, so I'm only using linear space. That gets me the number down here. Now, if I want the, if I actually want to find the sequence of edits, it's a little bit trickier, but we did that, we saw that a little bit with, in the last class when, yeah, we were keeping some list, I forget. But basically, you keep, for these cells, you can sort of keep an idea of the edits, the best paths that get you there. And if you're sneaky about it, you can still sort of use it a bit. So the simple thing is you can compute the edit distance using quadratic time and linear space. And if you're sneaky about it, you don't actually need. But it's hard to use linear time if you're actually trying to get the strategy. You can do it. So, but we actually do align big things, and we don't do it in quadratic time because it would be insanely slow. So I'm going to tell you about a trick. I have to start this again, except I'm going to run out of time anyway, so I won't start. I'm going to tell you about a trick that you should know just for when it comes up, because it can make your program significantly faster. It's called banded dynamic programming. So usually, when we're computing the distance between two strings, we're computing the edit distance between two strings which are similar. Because if they're really different, then we don't usually care how different they are. I mean, we don't compare random strings usually. Usually we're comparing like a genome of two humans, or a human and another mammal, or something like that. You're usually not comparing two completely different strings. So the thing is, if I asked you about the cost down here. Okay? So I'm far off the diagonal. So here I'm asking about changing a string of length 5 into a string of length 1. Well, let's say to make it interesting, into a string of length 2. Well, that's going to be at least to change a string of length 5 into a string of length 2, you at least have to get rid of 3 characters. So the edit distance has to be sort of at least the distance from the diagonal, right? Because you at least need enough edits to make the lengths the same. So it means that everything that's far off the diagonal has high cost, right? The edit distance, all of these entries that are way off the diagonal have to be big. They have to be at least the distance from the diagonal. So if I tell you that the edit distance between Canada and banana is small, is say 3 or less, is actually 2, but I say I'm not interested in what the edit distance is if it's more than 3, then you don't have to fill in the parts of the matrix which are further than 3 from the diagonal. And so that actually, if I tell you 3, if you're sneaky, you can rewrite your program so that it only fills in this band along the diagonal. It's called banded dynamic programming. And then if I give you the edit distance as k, you can actually do it in k times n time. I don't know if that will ever be useful to any of you, unless I put it on an app or something. But sometimes, like, banded dynamic programming can really make your programs a lot more efficient in real life. And if you're doing things like computational genomics, which is important and like saves lives, it's important to know this kind of stuff. Okay. Now I have like 15 minutes to teach you optimal binary search trees, which is a bit crazy. Oh, I have 22 minutes. Excellent. Except the camera is going to die because it's very hard to get SD cards, so I'm limited to 8 gigabytes. So it only records 7 minutes. But we'll have the collaborate ultra. So everyone knows what a binary search tree is, right? Good. I could, if I were sneaky, I would get ready and ask a question just before taking a drink of tea. So we saw in the lecture about Huffman's algorithm that you were trying to build an optimal prefix-free code. So you're trying to build a tree where you had weights at the leaves and the expected depth should be small. Well, suppose that somebody gives us a set of keys, but a set of keys, and asks us to build a binary search tree. And we know the frequency for which they work, they search for those keys. Well, we could just build a binary search tree, like any binary search tree, like you learned how to do in 2110. You could make it balanced, you could make it logarithmic type. Okay, so what is the worst case search time? It's like logarithmic. Okay, but that would be kind of, that might be suboptimal because it could be that one of the keys, they search for one of those keys a lot. So if we were completely free, we would put that at the root. In fact, if this didn't have to be a search tree, if this just had to put them in a tree, in a binary tree in some order, obviously you should put the most popular thing at the root. And the second most popular thing is one of its children. And the third most popular thing is the other of its children, and so on. So you just build a heap, a complete binary tree, and you just fill it in the order of popularity. But that's not generally going to give you a binary search tree, because it's a search tree, it has to be lexicographically ordered. So now I'm going to check because of, yeah, okay, this is good. I can open this. Good. Okay, so suppose I'm reading. I guess I could share the screen with you, but this is just a notes. So I wrote this last year. Here, I'll share the screen. So I did not last year. Well, yes, last year in 2019 when I was teaching the fall course. Okay, so suppose you're trying to build a binary search tree for the. Can people see this? Why is my screen flickering? Okay, so Apple. Hide this. Yes, okay, people can see this. Okay, so we want to build a binary search tree for apple, banana, grape, kiwi, orange, pear. So I'm always, this is an accident that before I was talking about vegetables and now I'm talking about fruits and I'm eating my breakfast. I'm not that obsessed with food. Maybe I am. But okay, so if apple has probability 13, and banana is probability 12, grape 15, kiwi 5, orange 12, pear 10, raspberry 8, strawberry 9. Okay, then the expected depth, apple, I'm going to get to apple. To get to apple, I'm going to do I'm going to go down 2 levels. But then, orange is at the root, so it's, right, no, 13. What's 2 times 13 plus 1 times 12? Oh, okay, no, sorry, banana is 12, yes. So banana is depth 1. So apple is depth 2, banana is depth 1, kiwi is depth 3. Okay, so the expected depth is 1.93. Okay, so if somebody searches in this binary search tree, the expected depth is 1.93. Can you do better? Can you rearrange the keys to get a smaller expected depth? Because then your binary search tree, you're going to, in general, the searches will be faster. Okay, so the greedy algorithm doesn't work. We don't have time for me to show you why it doesn't work, but it doesn't. But dynamic programming does, okay? And I'm just going to switch this back. So, we don't have I don't have enough time to teach this properly. But the idea is, you're still going to use this idea of, you can ask, you have this weak-willed professor who will tell you the answer to sub-problems, but will just not tell you the answer to the whole thing. Okay, so you have, can we build BST where the in-order traversal will priority increasing order? But that would be not, no, in general, no. Because here, in order, it has to be a binary search tree. So the keys have to appear in lexicographic order. Like in that example, it was apple. Apple starts with an A, so it has to be leftmost. So it's A, B, K, G, O, apple, banana, kiwi, grape, orange, pear, raspberry, strawberry, tangerine, watermelon. They have to appear in that order, and I'm not allowed to change the probabilities. So no, in general, no. I mean, if they happen to, I mean, if the probabilities happen to be very nice somehow, then the problem is easier. But so there's an easy way to do this. Well, okay, an easier, slow way to do this. And then if we have time, I'm going to show you how to do this. It's easy to see how to do this in cubic time. And then I'll try to show you how to do it in quadratic time, if we get there, if people follow me. So the idea is you want to know what is the best binary search tree for those keys and those probabilities. But you don't know how to do this. But you have this weak-willed professor. So what you can ask the professor, well, your binary search tree, it has to have a root, right? It's going to have some key is going to be at the top, right? And then it's going to have a left subtree and a right subtree. The left subtree could be empty, and this could be apple, and everything else is in the right subtree. Or the left subtree could be everything except, like, what was it, strawberry. So this could be watermelon, and this could be apple to tangerine. But empty subtrees are still subtrees. So I'm not going to prove it, but it's not hard to figure out. If this is the optimal tree, so let's say that, pick something, raspberry. Suppose the best, consider all the trees that are rooted at raspberry. Strawberry to watermelon. Then this is an optimal tree for the set of keys from strawberry to watermelon. The dots actually just represent tangerine. These notes are posted on Brightspace under lecture 10. Yeah, so they're up there. This is also going to be an optimal tree for apple to pear. So what I'm not proving is that the subtrees of an optimal tree are themselves optimal. Okay, it's not hard. It's like, okay, suppose that you had an optimal tree, and one of these subtrees was suboptimal. If you replace it with the optimal tree for the keys in that subtree, then the cost doesn't go down. The cost doesn't go up. It goes down. So if you decide, okay, I want to root my tree, is this still recording? Yes. Wow. If you decide you want to root your tree at raspberry, then your left subtree will be an optimal tree for apple to pear, and this will be an optimal tree for strawberry to watermelon. Okay? So, I'm switching back and looking at the Brightspace now. So, how do you use your weak-willed prof to find the optimal binary search tree? there's a for loop involved. How do you find the optimal binary tree that's rooted at Raspberry? Remember, you have this prof who will answer your questions about trees of sets of keys of size up to size n-1. So your weak-willed professor, I'm losing people already. Well, maybe not. Okay. Your weak-willed professor will tell you this is size less than n, because even if this were empty, this is a key. So this would be size n-1. It's actually, this is not empty, this is size 3. You have a fourth key up here, so this is n-4. So you can ask your weak-willed professor, Prof, what's the cost of an optimal tree on apple to pear? And your prof says, oh, well, it's this. Okay. And then you can say, oh, well, what's the cost of an optimal tree on strawberry to watermelon? And your prof says, oh, well, it's this. And so if you know that, say, this has probability 0.3, and this has probability, let's say this, ignore probability, this has weight 0.3, this has weight 0.1, this has weight 0.15, this has weight 0.15. Notice it's not like a Huffman tree in that you can just arbitrarily switch because you have to maintain the order. Then you can say, well, if these are now a subtree, the cost of this whole tree is going to be the cost of the expected depth of this tree is going to be sort of this plus 1, because now you're taking this tree and moving it down, and then plus this plus 1, and then this is at the root. Okay? So it's going to be the sum, it's going to be the cost of this tree plus the sum of the weights in this tree, because you're dropping it by 1 level, you're increasing all the depths by 1, plus the cost of this tree plus the sum of the weights, and then this doesn't distribute because it's multiplied by its depth, which is currently 0. Okay? So if you've chosen, if you really want to have raspberry at the root, then you can ask your weak-willed professor, and it stopped recording. And okay, so now we have the rest of it in only the high definition of the super cool webcam. Thank you, Andrew. I don't think anybody else from the faculty will ever watch these videos, but in case Andrew ever is watching, thank you, Andrew. So, how do you then, but maybe the best thing at the root is not raspberry. Maybe it's pear. What do you do? For loop. You ask your professor for every possible root. You ask your professor, so if it's not apple to pear, it could be pear is orange is before pear. This could be apple to orange. This could be pear. And this could be raspberry to watermelon. Okay? Are people people still listening? Okay, so that seems not hard, right? Okay, so that's the case if your weak-willed professor will answer about trees of size up to n minus 1. Key sets of size up to n minus 1. But, I have 4 minutes. But then what if your professor is getting slightly grumpy by being asked all these questions and stops answering it will only answer for sets of size up to n minus 2. Well, how do you then ask about if this goes down to tangerine? How do you ask about let's say n minus 3. So this is tangerine. Okay, let's do this. No, n minus 2, watermelon. So this is now empty. How would you figure out what this caused? This is now empty. But now, to figure out the cost of this, the minimum cost of this tree from apple to tangerine, this is of size n minus 1, but you don't have the professor. He isn't answering questions about sets of n minus 1 because he hasn't had enough tea. He's thirsty. Well, what you can do is consider this subproblem and look at all the possible ways to choose a route from apple to tangerine, and split these into two subtrees, and then you can ask about those problems. So but again, your professor is friendly, but is going to get annoyed if you keep asking the same question over and over again. Because, for example, remember, okay, so I'm running out of time, so I'm just going to skip the, so I'm going to skip the example where it shows why you would ask the same question over and over twice. It's in the notes that I wrote for the fall semester. I am going to, in 2 minutes, I'm going to quickly sketch. So the idea is, it's in the notes. The idea is to fill in, you're going to have a matrix which is n by n, right? And what it's going to be is one dimension is going to be the left key. So you're going to fill in the minimum cost of binary search trees on sets of keys, not subsequences. These now are continuous. You're going to fill in the minimum sequences, and it's going to be IL is going to be, or no, IS. I is going to be the leftmost key, the index of the leftmost key. S will be the size. So it's in the notes I posted, and I actually posted the little C code that actually fills in this example for these fruits that I wrote up. Because I want to put this on, I want to use this later, I want people to know, so people can leave, but I'm going to keep recording this. I want you to know why. So if you just do this, you're filling in a quadratic size matrix. So it's an n by n matrix. And to fill in the ij cell. So this is, let's say, this is the size of the subtree in this dimension, and this is the leftmost key. Right. To fill in some fill in some cell ij, you're looking at so let's say this is well no, let's say this is is. So this is actually backwards, whatever. Now you're looking at the subtree. You're looking to build a binary tree that goes from the ith key to the key that's I plus s minus 1. So you're looking for the cost of these. So in general, in general, what you're going to do is look at all the ways you're going to go from all the choices of root from I to I plus s minus 1. And you've already filled in that part of the matrix because it's sort of above, the size is small. When you look at a root, it splits into smaller subtrees. So you've already got it filled in because you fill this in order by row, by size. This one, it is, I don't know how you would do that. I don't know if you can reduce this. You can't reduce the space as easily. Maybe you can. Maybe it's going to take quadratic space. I don't know if there's a way around that. But it doesn't. It's not as easy as with edit distance. But this is going to take. It's a quadratic. It's an n by n matrix, and in general, for each of these cells, we're going to be looking at all the ways to choose a root. So it's going to be 3 nested for loops. For s from 1 to n, for I from 1 to n, and for, well, actually for I from 1 to n minus s, plus or minus 1. And then for each root, you have for the root from I to I plus s minus 1. So that's going to give you cubic time, which is not bad for a binary search tree of 100 keys. It's going to take like 1 million operations, but on a decent laptop, you won't have time to stop and take a drink of your tea before it finishes. But cubic time is pretty bad if you're looking, because 100, it's 1 million operations. 1,000, it's 1 billion operations. It's still pretty fast. If you have 100,000 keys, so what, that's 10 to the 5, that's 10 to the 15. That's starting to get pretty bad. If you have 1 million keys, that's 10 to the 18. That's going to be really noticeable. Then I would definitely have time to drink my tea. And unfortunately, I think the Collaborate Ultra session may stop at 1 o'clock and stop recording, but I'm going to keep talking just in case it doesn't. Otherwise, I will write up something. Okay, so how do you speed this up to be in? You can leave. If you want to leave, you can leave. And if it records, then you can see it later. How do you speed this up? Well, the speed up, the classic paper, so it's sped up to linear quadratic time. It's not known if you can do better than quadratic time, I think. I think this is one of those problems that I think quadratic is the best we know, or like quadratic possibly over polylog terms, polylog factors. So it was sped up to quadratic time by Knuth. So the asymptotic notation, Knuth is sort of the master of asymptotic notation. He's sort of the master of computer science. If people have been using LaTeX for doing their scribe notes, LaTeX is based on tech. Knuth wrote tech. He sort of just stopped and wrote tech because he wrote a book and he sent it off and it came back typeset and he didn't like how it was typeset, so he sat down and wrote typesetting software. I have a set of books over there by Knuth, The Art of Computer Programming. He used to, it doesn't say it now, but he's a professor at Stanford who looks like Yoda, actually, now. And it's not just me saying that. But it used to be that Google, if you search for certain people at Google, if you type their names into Google, it would pop up on the side of the search and would say, by the way, Google is hiring. So I know computer science professors who were sort of flattered that if you search for their names, Google would make you, would try to recruit you. Knuth was not one of those people. It doesn't do this now, but it used to be Knuth was the only one where the only one I've ever heard of, if you typed Don Knuth into Google, usually it gives you snippets of web pages, but it would give you what looked like a snippet, but it would give you a snippet that he never had on his web page. It would say, the man himself. Computer science wouldn't be what it is without him, etc., etc. And then you would click on it, it would take you to his webpage. And of course, he never put on his webpage the man himself. That was Google being funny, but they stopped that now. Knuth sped this up to quadratic time with a nice observation that I don't have time to prove, but it's sort of intuitive. So he observed that if you have an optimal binary search tree, so this is for keys ki to kj minus 1, and this is kj, and this is kj plus 1 to k sub, oh yeah, what is this going to be? This is going to be x, not k. X sub k, because we don't want k sub k. So he said, if you've worked the optimal binary search tree for xi to xk, and it's rooted at x sub j, and then you want to work out the optimal binary search tree for xi to xk plus 1, and you work out it's rooted at xj prime. If you add stuff on the right, the optimal root can't move left. So it can't be the case that you come in and say, I'm going to add stuff on the right, and then you find out that actually in that case you should move even more stuff from the left to the right subtree. That doesn't happen. So this is j prime is greater than or equal to j. So in that case, what you have for this because the black marker is dying. Yeah, people are leaving. Okay. What you have is, if you want to work out the optimal route for, let's say that to compute the optimal route for the keys xi to xk, let's say that that's r sub I k. So you just have to scan from, you don't have to scan all of the possible routes from I to k. You only have to scan the routes from the optimal route for r I k minus 1 to r I plus 1 k. Because you take this, you're looking at this set of keys, it's this set of keys with something added on the right. So you know that this optimal route doesn't move left. And you know that this can't be to the left of this, and it can't be to the right of this. So actually, you only have to search in this range, which means this is turning into a really long lecture. I'm sorry. Possibly it's not recording. But I want to have this posted. So that means that what you're having is I and sort of k, then you're looking at, to compute rik, the time you need is ri plus 1 k minus, because this is going to be to the right of this, or equal, minus ri k minus 1. So the total time is going to be this. It's going to be something like this. And this sum collapses, because what you can do is turn this into ri k of ri plus 1k minus sum over k of ri k minus 1. And then you show that this sums up to something which is only about n squared bigger than this. And so that's how you get it in quadratic time, by using this nice observation that if you add stuff on the right, the optimal route can't move left. So there's a reason I want to get this recorded. Thank you for your patience in waiting like an extra 15 minutes. But so this is, I need to have a video of this somewhere. So the idea is just you change it so that you keep track of what the routes are, and then you just scan scan between the optimal routes. That's not in those notes, so I want this video to happen. Thank you. Sorry about the delay. Well, the overtime. Thanks. Okay. Have a good weekend. It's too late to say good luck with the assignment, but I hope the assignment went well. Okay, and now, yay, that's quite a heavy day. Thank you. Okay, I will stop the recording now.